All right, let's just jump right in. We have all been there, right? You're following your GPS and all of a sudden it thinks you're driving through a building. Or maybe a call just drops even though you've got 5 bars of signal. You blame your phone, you blame the network. But what if the real culprit is 93 million miles away? Let's talk about why the sun sometimes just decides to break our tech. And just so you know, all this information we're diving into, it comes from somewhere solid. This is the third part of our 10-part explainer series, and it's all based on a really detailed technical report from the folks at RFI Detectives who are part of Virtualization Options LLC. We're breaking down their findings on how all this space weather really affects our day-to-day lives. So let's get back to that moment of frustration. You're driving, everything's fine, and then, poof, your navigation is useless. And look, it's not just some minor bug. Depending on where you are, that can be a genuine problem. So the real question is, what is this invisible force that's causing all this chaos?
Well, the problem starts with a massive event on the sun, and it flies across the solar system at an unbelievable speed. We're talking about a kind of menace that gives us absolutely zero time to prepare before it hits us.
And that menace is called a solar flare. Now, it's really important to get this straight. This is not a physical chunk of the sun flying at us. Not yet, anyway. It's a huge blast of pure energy, electromagnetic radiation. Think of it like the blinding muzzle flash from a giant solar cannon. And the most dangerous part of that flash is a powerful wave of X-rays.
And because this radiation is basically light, it travels at the speed of light. It crosses that 93 million mile gap between the sun and Earth in just over 8 minutes. Now think about that. That means by the time our satellites even see the flare happen, that radiation is already hitting our atmosphere. There is no advance warning. None.
So, this 8-minute-old radiation hits us, then what? Where does it actually do its damage? Well, the scene of the crime is a part of our very own atmosphere, a layer that is absolutely critical for all of our modern communications.
Way up there, our planet is wrapped in this electrically charged layer called the ionosphere. It acts like a giant radio mirror in the sky. Signals from GPS satellites have to travel down through it to get to your phone. And other long-range radio signals actually bounce off of it to get around the curve of the Earth. It's a fundamental piece of our global communication network.
So, when that blast of X-rays from the solar flare slams into the ionosphere, it just dumps a tremendous amount of energy into it. It supercharges the whole layer, making it way denser and way more chaotic for any radio waves trying to get through. A signal that normally has a clear path now has to fight its way through what's become a thick, crackling electric fog.
And this big disturbance up in the ionosphere creates two major headaches for our technology. They have two very different effects, and they're known as radio blackouts and ionospheric scintillation.
This is such a big deal that scientists actually have a formal scale for it, the R1 to R5 radio blackout scale. It's a direct measurement of the X-ray intensity coming from a flare. A small R1 event might just cause a few issues for ham radio operators, but as you go up that scale, the impacts get way more serious, leading to major GPS problems and even radar interference.
And in a real worst-case scenario, an R5 event, which is the top of the scale, it is powerful enough to basically absorb high-frequency radio waves completely. For airline pilots, ships at sea, or emergency crews in remote areas who all depend on HF radio, it's like the sky just goes completely silent for hours on end. The other effect, scintillation, is the one that really messes with your GPS. Instead of just absorbing the signal, that turbulent, supercharged ionosphere makes it flicker and fluctuate like crazy. The signal isn't totally gone. It's just so scrabbled and distorted that your phone's receiver can't get a stable lock on it.
So, here is the absolute best way to think about the difference between the two. A radio blackout is like a thick, dense fog. The signal just gets absorbed. It can't get through. Scintillation, on the other hand, is like trying to see a coin at the bottom of a shimmering swimming pool. The image is there, but it's so warped and wavy you can't make out what it is. To put it simply, blackouts kill HF radio and scintillation kills GPS.
Okay, so we've got these two big effects happening way up in the atmosphere. But how does all that science translate into that very real, very annoying glitch on the device that's in your hand or in your car? It all connects directly. That scintillation is exactly what causes your GPS to lose its lock or suddenly tell you you're 100 feet off the road. And here's a cool fact you might not know. A lot of modern cell networks, especially those using voice over LTE, they depend on super precise timing signals from GPS satellites just to work. So when that timing signal gets scrambled, your calls can drop.
And of course, for aviation and ham radio, the effects are immediate and sometimes pretty severe.
So, the crucial takeaway here is this. We live in this amazing web of technology that is deeply, fundamentally connected to what's happening in space. An explosion of energy on the sun travels at the speed of light, messes with our upper atmosphere, and that disturbance directly causes the electronics in our pockets and our cars to fail. It is a direct cause and effect chain that stretches clear across the solar system.
And that brings us to one final, kind of unsettling thought. Everything we've talked about so far was caused by the radiation from a flare, the light that gets here in just 8 minutes. But these flares are often just the opening act for something else. A massive eruption of solar plasma, the actual physical stuff of the sun, that travels much, much slower. So if the light is this disruptive, what happens when the blast wave itself finally gets here? Well, we'll get into that in our next explainer.